So we're looking at metathesis reactions. We're looking at specific pattern metathesis. We're looking at the metathesis double replacement. Double replacement has the pattern AB plus CB yields AE plus CB. We're looking for the driving forces. What were the driving forces for metathesis? We're looking at for at least one of three. Yeah, stronger acid to weaker acid. What else? Precipitation. And acid base would be this, stronger acid, weaker acid. We just looked at that. Oh, the types of reaction. No, this is for double replacement. What are the three driving forces for double
Gas
replacement?
formation.
Gas formation. So, I think we did an example of precipitation. Is that correct? Yeah. So, we could take a look. Something like this next example. Let's do lead to acetate and sulfuric acid. We'll just do some examples, some more examples here. And so we need the formula for lead to acetate. Does somebody have it? Lead is Pb. Acetate is what? Yeah, there are two ways. Normally when we do double replacement, we'll do it like this: 2,3,2, C2H3O2 minus. And so how many acetates do I need? That is Pb2 plus. So for every lead, I'm going to need how many acetates? 2. And then sulfuric acid, what's the formula for sulfuric acid? H2SO4. Sulfuric acid is H plus and then the sulfate anion. So what we're going to do is we're going to switch anions. So we're going to get the lead with the sulfate and the H plus with the acetate. So what forms here? Well, we're going to get lead 2 sulfate, which is going to have the formula. Well, they're 2 plus and 2 minus, so it's 1 to 1. PbSO4. And then an H plus with an acetate, that's a plus 1 minus 1, so it's just going to be 1 to 1 also. Like that. We don't worry about balancing until the end. We just want to get the formulas correct. So, for example, I have 2 acetates here. I don't worry about having 2 acetates here. I just want to make sure the ratio of cation to anion is correct. Ratio of cation to anion is correct. Before I even bother balancing it, I want to make sure there's a driving force, because if there's no driving force, there's no point in balancing this. So is there a driving force present for this? Okay, one is a precipitate. Which one's going to precipitate? Yeah, PbSO4, because sulfates are all soluble except for silver, lead, mercury. It actually goes silver, lead, mercury, mercury, calcium, strontium, barium. So this is a solid. And so we do have a driving force. It's precipitation. But we also have one more driving force. Do you see the other driving force here? Yeah, we're going from a stronger acid, which sulfuric acid is, to a weaker acid, which is acetic acid. This is acetic acid here. Acetate forms acetic acid. And therefore, we should balance it. The way I balance it by ions. So here I have 1 lead. Over there I got 1 lead. Here I have 2 acetates. I need 2 acetates here to double that. 2 H's, 2 H's, 1 sulfate, 1 sulfate. So this is balanced here. All right, this is what we call the CE. And then we're going to go to the IE. The IE, what do we do for the IE? We ionize the strong electrolytes. So remind me, what are the strong electrolytes again? electrolytes are they? They're good conductors. How do you recognize what types of compounds are strong electrolytes? Soluble salts. You know, hopefully if you review it every day, like the strong electrolytes, you know, soluble salt, what else? Strong acid, strong base. If you review it every day, it will come easier. Right now, if it's taking this long to come up with a soluble salt, it's taking too long. You know, you want it to come faster. This is for your benefit. It's not for me. Continue harping on you to do it. But for any class, you know, rather than once. A lot of people, you know, think about how much advantage you'd have between you who reviews it every day versus somebody who crams it the night before the test. You know, it only you can only cram up to a certain point. But anyway, lead-2 acetate. All acetates are soluble, so this is a soluble salt. We're going to ionize it into what? The charge is very important. If you don't have the charge there, it's not correct. And acetate, how many acetates? 2 acetates. So we got to make sure it's correctly balanced. For every PV2 plus, we're going to split off 2 acetates. Now this one's tricky. This one we think is going to split up into 2 H pluses plus a sulfate, but that's not the case. It only breaks up one at a time. No matter how many times I say this, there's always going to be like a proportion of students who will always get it wrong, no matter what. But it breaks up into H plus and HSO4 minus because one breaks off at a time, and HSO4 minus is not a strong acid. Only strong acid is completely ionized. This is a weak acid. Weak acid. It's one of the stronger weak acids, but it's still a weak acid, so we just leave it alone. We only break up the strong acids. How about PbSO4? PbSO4 is an insoluble salt, so we leave it alone. If it's not a strong electrolyte, leave it alone. And then acetic acid, is that a strong acid? No, acetic acid is not one of the 7 strong acids you memorize, so you leave it alone. If it's not strong, leave it alone. And so when we look at the spectators, are there any spectators here? Like for example, did lead-2 react? Yeah, it precipitated. Did the acetate react? The acetate did react because over there we have acetic acid. We don't have free acetate. And so the NIE is the same. And so this is the IE and the NIE. So this is an example of where we have both precipitation and stronger to weaker acid, but we only need one driving force to make it happen. And, that's it. All right, let's look at another example here. Okay, the next example we're going to look at calcium carbonate and sulfuric acid. Okay, what's the formula for calcium carbonate? CaCO3. Because calcium is a 2 plus, carbonate is a 2 minus, so just a 1-to-1 ratio works for that. Is calcium soluble or insoluble? Phosphates, carbonates, and chromates are insoluble, except for group 1 and ammonium. So this is insoluble. We have to put solid here. Sulfuric acid, of course, is okay. It's the same here. So forth. So what's going to happen? It's going to form calcium sulfate and hydrogen carbonate. So calcium sulfate is C8SO4. So this is 8 plus and SO4 2 minus. And then hydrogen carbonate, well, hydrogen's plus 1, carbonate's minus 2. So how many hydrogens do we need for that? 2. Hydrogen carbonate also goes by the name of what? In fact, this is the name we should use. No. Hydrogen carbonate ion does, but this is hydrogen carbonate, the compound. So hydrogen carbonate, the compound, the name for that is, what's the acid name? Carbonate is carbonate ends in ATE, and so the acid's name would be carbonic acid. That's correct. Carbonic acid. Carbonic acid. What do you have memorized for carbonic acid? It's unstable and it decomposes into what? Yeah, good. Water and carbon dioxide. So this is a gas former. And so what we say is gas formation is a driving force. But also, what is calcium sulfate? Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. This is insoluble solid. But it's tricky here because on the one hand we have a precipitate, on the other hand we're getting rid of a precipitate. And so this is a tricky, this is a solid to solid. Requires more analysis. Whereas this one, this is aqueous forms a solid, so we're going from liquid to solid. So for sure this is a precipitation. However, here we're dissolving one solid and forming a new solid, so that requires more analysis. Whereas if this were aqueous and aqueous, then for sure it's a precipitation. So solid requires more analysis. This is why your book avoids this kind of problem, but it's okay. All right, so this is the CE. The IE, we're going to go ahead and 180 will be. But we have a driving force, so all we need is one driving force, the gas, so we're okay. Calcium carbonate, do we ionize it or leave it alone? Well, we ionize soluble salts. Is calcium carbonate a soluble salt or insoluble salt? Insoluble. So if it's insoluble, just leave it alone. Sulfuric acid, ionize it or leave it alone? Yeah, we ionize it H plus and HSO4 minus. So doing it twice here. Plus and HSO4. This is for the ionic equation. And then calcium sulfate, do we ionize that? No. It's correct. H2O, do we ionize that? No. CO2, do we ionize that? No, because we only ionize the soluble salts, the strong acids, and the strong bases. That's it. That's, you should have memorized. So we have some examples here. The examples of precipitation, stronger acids, weaker acids, gas formation. Just a few examples of those. What if we have none of those? Let's do the next example. So the next example is going to be sodium bicarbonate. And potassium phosphate solution or mix. So if we mix sodium bicarbonate and potassium phosphate, let's see if we get anything happening. So, what's the sodium ion? Okay, Na plus. Bicarbonate is HCO3. What's the charge? Minus. So it's a 1-to-1. So NaHCO3 works. Plus potassium phosphate. Potassium is K plus. Phosphate is what? PO4, right? PO4, 3 minus. So we'll need 3 potassiums, K3PO4, and that should do it. So what are we going to form? We're going to form sodium phosphate. So what's the formula for sodium phosphate? What's the correct ratio of ions? Yeah, 3 NAs. So Na3PO4 plus potassium bicarbonate. So potassium bicarbonate is 1-to-1, so should be all right there. Is bicarbonate unstable? Is it going to decompose into gas? No. Carbonic acid does. Bicarbonate's okay. Carbonic acid does. Bicarbonate's not. And so we don't have gas formation here. Let's look for a precipitate. Will sodium phosphate precipitate? No, because sodium phosphate is group 1. Group 1s are all soluble, so this is aqueous. How about potassium bicarbonate? Will that precipitate? Again, no, because this is group 1. All sodium salts and all potassium salts are soluble. And then we look, are we going from a stronger acid to weaker acid? Well, nothing's changed. We start off with bicarbonate, we end up with bicarbonate. We have phosphate, we end up with phosphate, so there's no change. So do you see any driving force for this? We have no precipitation, no gas formation, and no stronger acid to weaker acid. Therefore, there's no driving force. If there's no driving force, what we say is NR. NR stands for no reaction. But this is no reaction. We only looked at one type of reaction. And what type of reaction are we looking at? We're looking at metathesis. And so what we should say is there's no reaction for metathesis. But it could mean that there's potential, there could be what were the other 2 types of reactions? Acid base and redox. All right, so what we're gonna do is we're gonna look for potential acid base next. There are two types of acid base we look for. One is Bronsted. Bronsted or Bronsted-Lowry. The acid is an H plus donor. The base is an H plus acceptor. That's Bronsted-Lowry. And then two, we look for Lewis. For Lewis, the acid is an electron pair acceptor. We haven't gotten to electron pairs yet. And the base is electron pair donor. I'm going to talk about Lewis later. For right now, what we're going to do is we're going to focus on Bronsted-Lowry acid bases. Because we know hydrogen ions can be transferred here. All right, so if we do the Bronsted analysis, we transfer just one proton at a time. So this is different. There's some overlap with metathesis. So in metathesis, we complete. In metathesis, we do complete reaction. In Bronsted, we do it step by step. And so let's just take a look at one example: H2SO4 plus sodium hydroxide. In metathesis, we have H plus and sulfate, and sodium ions and hydroxide ions. So this is how we'd handle something like this. We do H plus and OH minus. H and plus and OH minus, hydrogen hydroxide. What's hydrogen hydroxide called? It's just water, H2O. And then we do sodium with sulfate. Well, sodium with sulfate is Na2SO4. And so what we need is we need two sodium hydroxides, two waters, and then that should be it. The driving force for this is going from a stronger acid, sulfuric, to weaker acid, water. In Bronsted, we treat this as, if we're going to do it, we treat it as a two-step process. So for Bronsted, we only transfer one. In this case, how many H pluses were transferred altogether? All two of them. For Bronsted, one step at a time. So one major difference is if we're using the Bronsted method, we would do H2SO4 plus sodium hydroxide first, and then what we'd form is H and OH would be water. H and OH would be water, and sodium. And in this case, we are only losing one hydrogen, and so we're going to form sodium bisulfate, or hydrogen sulfate. Okay, in the next step, what we'll do is we'll take the sodium bisulfate and then add sodium hydroxide to that. And so what we're going to have is this. We're going to get rid of that last hydrogen. So we'll have H2O plus sodium sulfate, like that. So we would have done it in 2 steps. So the first hydrogen is taken off in step 1, and the second hydrogen is taken off in step 2. Which means if we could do it by metathesis, it's just easier. The preference is to do a metathesis if available. Use a metathesis way if possible. In this case, it's possible. We could just treat this as a AB plus CD type reaction. However, in that last reaction that I just written up, it's not possible. We can't do a metathesis. The metathesis doesn't work. And so if there's overlap, then we're going to use metathesis. If there's no overlap, then we're going to have to use the Bronsted method for doing this. The Bronsted method is not difficult. Just take some practice. So the Bronsted method is like this. One, we're going to inventory major species. So we have sodium bicarbonate and potassium phosphate. Both of these are aqueous. But to emphasize, I'll write aqueous here. And so if I have a beaker of sodium bicarbonate, what do I have? Well, it's a soluble salt. So I'm going to have sodium ions and bicarbonate ions. Is bicarbonate a strong acid? Strong acids lose their H+, or strong acids ionize. So is bicarbonate a strong acid? Should I ionize bicarbonate? Break it up. We break apart strong acids, so I'm asking you, is bicarbonate a strong acid? One of the 7 strong acids that you memorized? Yes? No. So bicarbonate is not a strong acid, so what we're going to do is just leave it together. If this were a strong acid, you break off the H+. This is not a strong acid, so you leave the H+ on there. It's stuck. Potassium, I'm not going to balance this. These are the major species. These are the major species in solution. What I have. Okay, the next step is to use the chart to ID the acids and bases present. Except I have one major species that's missing. Do you know what major species is missing? Did I post the acid chart? I forgot to do that. Post that. You know what major species is missing? one major species that's missing from this list. Do you know what it is? Water. H2O. These are aqueous. H2O liquid is missing. And so what we'll do is we'll just ID it. So sodium ions. And so we're going to use the chart to ID. Do you see sodium ions on the chart here? No. There's no. And so what we say is sodium ions are neutral. They're neither acid nor base. Neutral. Then we go to bicarbonate ions. Do you see bicarbonate ions on the chart? Yeah. What is it, an acid or base? On the left, we have our acids. On the right, we have our left side of the chart are the acids, the right side are the bases. So there it is. It's an acid. I'll label it A for acid. But if you read through this chart every once in a while, then you'll note that bicarbonate is also a base. So what do we call something that can be both an acid or a base? Do we have a name for it? Amphoteric. And so bicarbonate is amphoteric. And so I'm going to write A/B to indicate it can be either an acid or base. Now, which one is it going to be? It can't be both at the same time. It's got to be one or the other. What it is depends on what you react it with. So if bicarbonate's the strongest acid around, it's going to act as the acid. But if there's a more powerful acid around, then it's going to act as the base. And so it depends on what you mix it with. That's going to dictate how it behaves. Potassium ions. Do you see potassium ions on this chart? We already read through this chart. Do you remember seeing potassium ions? We read through it once, but once is not enough. People who read it once, they'll forget it. It's not that you have to have it memorized, but you should just know. So we're going to call it neutral. But just because it's not on the chart doesn't mean it's neutral. It might be acidic or basic because the chart is not comprehensive. We have a more comprehensive chart over there, but that's still not comprehensive. So we'll have to know a little bit more. Okay, phosphate. Is phosphate on this chart? Yes. What is it? A base. It's at the border. It's a weak base, but pretty strong for weak base. So, but we don't care about strong or weak yet. It's a base. Is it amphoteric? Phosphate cannot be amphoteric. What's missing? It can't be an acid because it doesn't have H. All right, hydrogen. You need hydrogen. An acid. So phosphate, and then finally water. Water is the example of an amphoteric species I gave you. It's both an acid and a base. So you can see water as an acid here. Not that great. An acid. It's not that great of a base either. It's up here. Water is what we call neutral as well, but it's what we call pH neutral. These are pH neutral too, but water can react. Because water can react, we call it both an acid and base. 3. Use the chart to determine the strongest acid present. If there's going to be a reaction, this doesn't mean there's going to be a reaction, but if there's going to be a reaction, the reaction is going to be the strongest acid reacting with the strongest base present. And so we have two acids present. Do you see the two acids? What are the two acids present? One is bicarbonate, the other is water. And so we're going to use the chart to figure out which one is stronger. So the strongest acid on the chart is HClO4. We'll just drop down until we see one. And I see it here. Do you see bicarbonate is here and water is here? So which one's stronger? Yeah. Bicarbonate is stronger than water. So bicarbonate is the strongest acid present, so that's going to act as the acid. It's a better acid than water. Or use the chart to determine the strongest base present. So we have three bases present. We have bicarbonate, phosphate, and water. So out of those three, which one's the strongest? So hydride's the strongest. And then we'll scroll up. You see the first base we hit is phosphate, which is here. And then bicarbonate's up there, and then water's way up there. And so the strongest base present is going to be phosphate. Okay, 5. In 5, we're going to do the reaction. And so, write the, I'm going to call it potential reaction because there's no reaction unless there's a driving force. By transferring one hydrogen, one H plus, from the acid to the base. Okay, so what I'm going to do is I'm going to write the acid here, bicarbonate, and then I'll write the base, phosphate. And then I'm going to transfer one hydrogen over here. And so bicarbonate's going to lose it, and phosphate's going to gain it. So what are the correct charges now? If bicarbonate loses an H plus, what's its new charge? Yeah. And if phosphate gains an H plus, what's its new charge? Okay. And so here we have the acid and the base. We don't know which way this reaction is going to go. So I'm going to put a little question mark here. Okay, 6. There really aren't that many steps. I'll just do them quickly, but I'm really breaking it down. Determine the acid and base going backwards. By which in reverse. So what we do is, if we go backwards, let's say, okay, going backwards, we have carbonate and hydrogen phosphate or monohydrogen phosphate. If we go backwards, who lost, who gained? The hydrogen. And so what we have to do is we have to imagine going in the reverse direction, starting with the products here. And I would see that, well, we go from hydrogen phosphate to phosphate, so that must have lost. And then we go from carbonate to bicarbonate, and that must gain. And so it's going to look like this. Bicarbonate's the acid, phosphate is the base. I'll draw 2 arrows here. And then going backwards, we say that carbonate is the base, and hydrogen phosphate is the acid. Recall that both bicarbonate and hydrogen phosphate are amphoteric species, so we don't know which way it's going to act unless we mix it with something. Here we mix it. Okay, 7. Determine the driving force that is going from stronger to weaker acid and stronger base to weaker base is present. And so what we have to do is we have to compare the two acids and see which one's stronger. Is bicarbonate stronger, or is hydrogen phosphate stronger, or monohydrogen phosphate? So we use a chart for that. Is bicarbonate stronger or monohydrogen phosphate? Which one's stronger? Bicarbonate stronger. And so we'll label this SA and this WA. Is phosphate or carbonate stronger? Well, remember it's inverted. So the acids increase in strength going up, the bases increase in strength going down. So which one's stronger, phosphate or carbonate? Phosphate. So this is stronger, this is weaker. It has to be strong, strong to weak, weak, or weak, weak to strong, strong. It's just the way it works. And so this is what we call a driving force. Oops, I was supposed to do it over here. So we're going to have a reaction. When bicarbonate and phosphate come together, there's going to be a reaction. And the reaction is going to form carbonate and hydrogen phosphate. And so we're going from stronger acid and stronger base to weaker base and weaker acid. So this is the driving force. So we do have reaction. Therefore, an acid-base reaction did occur. So we didn't see any metathesis, but we did see acid base. Okay, let's try another one here. solid sodium sulfide and aqueous sodium chloride. Let's just try that. What's the formula for sodium sulfide? Na2S. Good. And sodium chloride? NaCl. So first off, this is an AB plus CD. So if it's AB plus CD, then it should form AD plus CB. So the double replacement reaction, right? But if we did this, what would we form? We'd form sodium chloride and sodium sulfide. So basically, there's going to be no reaction. I mean, the products are the same. But I should say no reaction for what? Metathesis. There's no reaction for metathesis, but metathesis is not the only reaction type. There are two more, and therefore, let's look at the next one. So if we had no reaction for metathesis, then try acid-base. And so what we're going to do is, step one, what do we do? Yeah, inventory. And so what's the inventory here? Well, is sodium sulfide soluble? Are sodium salts all soluble? All sodium salts are soluble. It's a soluble salt. Soluble salts are strong electrolytes, weak electrolytes, or non-electrolytes? Strong. So what's going to happen is this is going to break up into sodium ions and sulfide ions. I'm not going to balance it because I'm just inventorying. Inventory just means, do I have sodium ions present? Yes. Do I have sulfide ions present? Yes. Sodium chloride, I'm going to have sodium ions and sulfide ions, and then sodium ions and chloride. I already have an inventory for sodium, so I know there's sodium ions present. Now I have sodium ions, sulfide ions, and chloride ions present. Do I have anything else present? I'm missing something. H2O. I got water present. I mean, this is aqueous. Aqueous means dissolved in water, so I have H2O liquid. Always water. There's always water present. Unless it's all gas or all solids, there's always water present. Okay, next what? Yeah, so sodium ions, do they occur on the chart? No, so we'll just say neutral. And sulfide ions, do those occur on the chart? You can see it on the bottom right there.
Yeah.
And so it's on the right side, we call it a base. It's not on the left. Chloride ions, do chloride ions occur on the chart? Do you see them? Way up here. Those are base. But you know, chloride ions are way too weak. Way too weak to act as bases in water. Let me put a little asterisk here. Chlorides are too weak to act as bases in water. So for example, let's say you ran out of antacid. If you ran out of antacid, say milk, magnesia or something, could you use table salt instead? You know, like you ran out of Tums, so somebody says, oh, you know, I need some antacid, but you say, I have some sodium chloride present. Sodium ions we know is neutral, but you know, sodium chloride has chloride, and you might go, well, chloride is a base, right? We see it's a base on this chart. Do you see it? And so you tell your friend, you know, why don't you use some sodium chloride instead of Tums? Would that be effective? It wouldn't be effective. Why? Because chloride is just too weak. Way, way too weak. In fact, it's going to do nothing to help them. And so I wouldn't give sodium chloride as a substitute for antacid. Water is more effective of a base than chloride. Maybe tell them to drink a cup of water, but it's not really going to help. Well, maybe it'll help dilute it. Okay, so water, as we saw, is amphoteric as before. Okay, what's next? Pick the strongest. Okay, well, we only have one acid. Since we only have one acid, picking the strongest acid is easy. It's going to be water. Okay, and then pick the strongest base. Which one's the strongest base? Sulfide. And so the reaction is going to be between water and sulfide. So let's go ahead and do that right here. And so if I take H2O liquid and sulfide, what forms? So what happens to the acid? The acid loses a hydrogen ion. So one H comes off, we're left with an OH or HO. What's the charge? Minus. And then this gains an H, so we're going to be left with HS. What's the charge? -1. Okay, now we don't know which way this is going to go, right? It's going to go left. We're looking at which way is downhill. And so this was our acid, this was our base. Now what we have to do is we pretend we're going to go backwards. Going backwards, which one is the acid, which one is the base? Going backwards. Here, in this case, we cannot use this chart because both of these are amphoteric. Hydroxide is both an acid and base, and HS minus is both an acid and base. How they react depends on the reaction itself. So when we go backwards, which one loses, which one gains? The hydrogen. Did OH minus gain a hydrogen or lose a hydrogen going backwards? It gains, so if it gains, is it the base or the acid? Yeah, OH minus is the base. Bases are proton acceptors, or the gain protons, or the gain hydrogen ions. Acids lose, so HS minus lost going backwards, OH minus gain going backwards. And so we have to assign the product, acid, base, if we were to reverse the reaction. Which reaction is going from stronger to weaker? Okay, well, we compare the two acids. Which one's a stronger acid, H2O or HS minus? So we look at the two acids. Which one's a stronger acid, H2O or HS minus? H2O is a stronger acid here. From the chart, we see that H2O is stronger, HS is weaker. Sulfide or hydroxide, which one's the stronger base? Sulfide or hydroxide? Sulfide's a stronger base. And so, again, we're going from stronger to weaker. Therefore, we see driving force. So it's favored this way. The stronger to weaker direction's forward. If we go weaker to stronger, the favored direction is reverse. and so therefore no reaction. In this case, we should expect reaction because we're going from stronger to weaker, and we should get reaction. So the reaction doesn't occur between sodium sulfide and salt. The reaction occurs between sodium sulfide and water. It's a sulfide reacting with water, and so we expect reaction here. And so indeed there was reaction. There's acid-base reaction present. No metathesis reaction. So I'm going to stop here and then we'll take a break.